Chapter 16 is on aqueous ion equilibrium. This is going to cover several other equilibrium situations involving aqueous ions. So more Ks and that sort of thing. So we're going to start by talking about buffers. A buffer is a solution that resists a pH change. The way it does that is by containing significant amounts of a weak acid and its conjugate base, or a weak base and its conjugate acid. The buffer range is plus or minus 1 pH unit of the pKa of the acid, or the pKb of the base if you're using a weak base. So by having significant amounts of a weak acid and its conjugate base around, if you add some acid, say a strong acid to the solution, it will react with the conjugate base and the pH isn't going to change very much because it gets used up. If you add some base, it reacts with the conjugate acid, pH doesn't change very much. It's able to shift and keep that pH fairly stable by having both acid and base around to react. So they apply Le Chatelier's principle to weak acid equilibrium. So if we add extra base, it's going to react with the weak acid and just form more of the conjugate base. If you add some acid, it's going to react and shift the other way. Either way, you're getting rid of the strong acid or base by just making water and then more of the conjugate. So here's going the other way, also contains a lot of the conjugate base that can combine with any added acid and make the weak acid, and so our concentration of H3O plus is kept constant. All right, if you can use the X is small approximation for a situation, you can generalize the situation for a buffer into this equation here, which is called the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation works when you have significant amounts of a weak acid and its conjugate base. Instead of working through the equilibrium situation with the Ka, you can just plug it into the Henderson-Hasselbalch, where you need to know the pKa of the weak acid, and then take the log of the concentration of the base over the concentration of the acid. That will get you your pH. So let's work through an example. Calculate the pH of 25 milliliters of 0.5 molar acetic acid combined with 20 milliliters of 0.5 molar sodium acetate. The pKa for acetic acid is 4.7. So what we're going to do is we're going to use first M1V1 equals M2V2 because we're combining these two things together. So for our HC2H3O2, our initial molarity is 0.50 times 25 milliliters is equal to M2 times 20 plus 25 is 45 milliliters. So our molarity of our acid is 0.278 molar. We can do the same thing for our C2H3O2 minus, where we have 0.5 times 20 is equal to M2 times 45. So here M2 is 0.222 molar. And then for my Henderson-Hasselbalch equation, I know my pH is equal to pKa plus the log of my base over my acid. So my pH is going to be 4.7 plus the log of 2.222 over 0.278, which is 4.60 is my pH, or 4.6. Now that should make some sense. So the pKa is equal to the pH when the two concentrations are equal to each other. So when you have equal amounts of acid and conjugate base, your pH will equal your pKa. Here we have a little bit more acid than we do base, so it makes sense that our pH is a little bit more acidic than our pKa value. That's a good double check for you. So here's another example for you that you can pause and work through. What is the pH of a buffer? That is 0.14 molar hydrofluoric acid. The pKa is 3.15, and 0.071 molar potassium fluoride. All right, so for this one, again, we're going to use the Henderson-Hasselbalch. So pH is equal to pKa plus the log of the base over the acid. So my pH is going to be 3.15 plus the log of my base concentration is 0.071 divided by 0.14. So my pH is 2.86. Again, it makes sense that it goes down because it's higher in hydrofluoric acid than it is in fluoride. All right. Now we're going to head towards our next topic, but what happens when we add acid or base to a buffer? So what's the pH of a buffer that has 0.1 moles of acetic acid and 0.1 moles of sodium acetate in 1 liter that then has 0.010 moles of sodium hydroxide added to it? Well, what we need to do is react the strong base with our weak acid and find out what our new concentrations are. So our strong base is going to react with our weak acid. We're not going to have any extra strong base around, but now we're going to lose that amount from our weak acid. It's going to react. So we're going to end up with 0.090 moles of our weak acid because it reacted with the strong base. And when it reacted with the strong base, it became the conjugate base. So we're going to have 0.110 moles of the conjugate base after the reaction. So when you've added a strong acid or base to a buffer, you have to react it with what's around, get rid of the strong stuff, and then figure out what your new concentrations are. So now we are left with new concentrations that we can just plug into our Henderson-Hasselbalch equation. We need to know our pKa of acetic acid, which I think we had a couple slides back, or you can look it up in a table. So the pKa of acetic acid is 4.7 plus the log. Now we have 0.110 moles of base, 0.090 moles of acid, and so our new pH is now 4.79. Or 4.8, since I just had one sig fig with my pKa. So working this through. Here, I'm giving my pKa at 4.74, so that's going to change it slightly. So if you plug in pH is 4.74 plus the log of 0.110 over 0.090, this 4 is going to change it slightly, so we get 4.83. But same concept. Okay, so calculate the initial and final pH after adding 0.010 moles of hydrochloric acid to 500 milliliters of a buffer solution that is 0.125 molar in acetic acid and 0.115 molar in sodium acetate, pKa 4.74, so we have that extra digit there. So go ahead and pause the video, work this through. Our initial is going to be 4.74 times 0.115, or sorry, plus 0.115 over 0.125 in using Henderson-Hasselbalch. So my initial pH is, there's a log right here, is 4.71. Then I'm adding 0.010 moles of hydrochloric acid. So I'm going to be reacting C2H3O2 minus plus H plus goes to, and actually here really it's just a straight arrow because we're getting rid of all of that H plus from there. HC2H3O2. We start off with, 0.125 times the 500 milliliters is 0.0625 moles. We're told we have 0.010 moles of H plus, and then our acetate is 0.115 times our 0.5 liters gets me 0.0575. Then if I fully react that to get my H plus, my excess H plus down to 0, now I'm going to have 0.0725 and 0.0475. Then I can either take into account my 500 milliliters again or not. It's going to wash out because there's division here, but let's just do that anyway. So 0.0475 in 500 milliliters gets me 0.0950 molar of that, and I'll have 0.145 molar of my acid. So now my pH is going to be my pKa 4.74 plus the log of, this is my conjugate base, so 0.0950 divided by 0.145 gets me a pH of 4.56. And again, it makes sense that we became more acidic because we're adding hydrochloric acid to our buffer. What about bases? You can also do this with bases. There is a correlating Henderson-Hasselbalch equation where the POH is the pKb plus the log of the acid over the base. It works the same way, so calculate the pH for a buffer. That's 0.050 molar ammonia and 0.20 molar ammonium chloride. The pKb is 4.75, so my POH is going to be 4.75 plus the log of the conjugate acid, 0.20 over the base, 0.50. So my POH here is 4.35, which means my pH is 14 minus that, which is 9.65.